Hi, my name is Lauren Grant, and this is my 2212 lab for circuits. So I'm gonna introduce you to the lab, tell you about some of my observations, the fundamental physics principles, the experiments and results, and then the follow-up question. The purpose of this lab was to use the principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. So some of the observations we made in this lab is that the system is circuits, the surroundings are everything else, and then the resistance of the 47 ohm resistor was 48 ohms, and in the 100 ohms resistor, the resistance was 102 ohms. And some of the assumptions we made is that the resistance in the copper wire is negligible, and that all the devices used to measure the current and voltage are accurate. The fundamental physics principles that we used in this lab included Kirchhoff's circuit laws, which include the node rule, which is the current in is equal to the current out, and the loop rule, which basically says that the difference in potential, like when you go around the circle in the loop, is equal to 0. And then Ohm's law, as well as capacitance. So in the first part of the lab, we were instructed to make a series circuit with two 1.5 voltage batteries, 2 ammeters, and then 2 resistors, one being at 100 ohms and the other one being at 47 ohms. And in this, we got that the series current is equal to 0.02 amps. And if we invert this backwards, so invert the ammeter backwards, it still reads 0.02 volts. And then if we replace the ammeter with a voltmeter, we get that the current is 0 amps and that the voltage is 3 volts. So this is where I calculated the resistance across the 47 ohm resistor and the 100 ohm resistor. And then we also found that in the wire the resistance is 0, and in the ammeter the resistance is 0. And then when the voltmeter is changed to be an ammeter, and parallel to the 100 ohm resistor, the ammeter changes to be 0.06 amps because the current is split at the node between two paths. In this part of the lab, we were instructed to create an RC circuit. We connected a light bulb, battery, and capacitor in series. This allowed us to see that the bulbs are bright as the current originally runs through it. However, the bulbs dim in light as capacitor charges. When we disconnected the battery from the circuit, we saw the capacitor discharge. And we once again saw the bulb light up and eventually dim again. When we used the 10 ohm bulb, we saw that it took 8 seconds for the capacitor to charge and 10 seconds for it to discharge. And then when we used the 20 ohm bulb, it took 12 seconds for the capacitor to charge and 20 seconds for it to discharge. So this is the time-dependent voltage across a discharging capacitor in RC circuits. Basically, in this part of the lab, we were instructed to create a series circuit using a 9-volt battery, a 200 microfarad capacitor, and a 30 ohms light bulb. We were to measure the voltage across the capacitor with a voltmeter, and then we were to set the capacitor to discharge and to plot 20 seconds worth of voltage versus time data, which is below. And then this is my linear equation using the natural log versus time graph that they gave us. And so my experimental slope ended up being negative 0.1676. And then you do this value, which is your RC. And so you do -1 over your RC value, which gave me 5.967 seconds. And so the expected value was 6 seconds. So the experimental value is very close to the expected value. It is off about 0.033 seconds, which is really close. We were doing this lab in real life and use an actual ammeter instead of an ideal simulator ammeter. What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? The current would be lower because a real ammeter would cause resistance would not be 0 like it is in the experiment. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? If there was no resistor present in the circuit, the current would flow directly into the capacitor without any time lag. This, however, would not happen in real life because the wire would still cause some resistance.